Right. Okay, in this video, we're going to talk about section 12-2, dealing with two-way ANOVA, and that will be the wrap-up of chapter 12. Now, already in the last video for section 12.1, we talked about one-way ANOVA, and that is where we test the equality of three or more population means by analyzing sample variance. And here we use this with data categorized with one factor or one treatment. In a two-way ANOVA, it's going to be a little bit different because now you're going to have two factors in three or more categories. Okay, so in this section, we're going to analyze sample data from populations separated into categories using two characteristics or two factors such as gender and eye color. And then we're going to apply the method of two-way analysis of variance to the following. That is a test for the interaction between the two factors, and then test an effect from the row factor and test for an effect from the column factor. So here in this section, just like section 12.1, where we focus on just interpreting the results from technology, we'll do the same thing here for section 12.2. Okay, so the only thing, you won't have to worry about doing any manual paper and pencil calculations. We'll be using StatDisk as a means of calculating the data set and interpreting the results from StatDisk. Okay, so this section does describe the method of two-way analysis of variance, which is used with data partitioned into two categories according to two factors. So here, the method of this section requires that we first test an interaction between the two factors, then we test for an effect from the row factor, and we test for an effect from the column factor. Okay, so here the table below is an example of pulse rates in beats per minute, which is categorized in two factors. One would be the age bracket in years, the other is in gender. Okay, so if you look at this, these rows represent the age bracket in years: 18 to 29, 30 to 49, and 50 to 80. And then your column factor is going to be these two columns: gender, which is female and male. Okay, so that's what we mean by using a two-way analysis of variance, or two-way ANOVA in this case. Because you got two factors here, three rows for the age bracket, and then two columns for the gender. Okay, now what do we mean by interaction? Is this: there's an interaction between two factors if the effect of one of the factors changes for different categories of the other factor. Okay, that's what we mean by interaction. All right, now we're going to explore this data in the earlier table by calculating the mean of each cell and construct a graph. The individual cell means are shown in the table that you'll see on the next page. And those means vary from a low of 64.8 to a high of 82.2. So they vary considerably. So here what they did is took the mean or the average of each of these cells that you see in this table, and it ended up like this. So these are the means here, based on the age brackets and the gender, female and male. Now we can interpret an interaction graph as follows. So here the interaction effect says, an interaction effect is suggested when line segments are far from being parallel. And no interaction effect is this. If the line segments are approximately parallel, it appears that the different categories of a variable have the same effect for the different categories of the other variables. So there does not appear to be an interaction effect, as you can see here in this graph here, this interaction graph. So those appear to be approximately parallel. Okay, now let's go into the two-way analysis of variance here, or the two-way ANOVA to be short. Okay, so we'll be testing an effect from an interaction between the row factor and the column factor, and test for an effect from the row factor and test for an effect from the column factor. There are some requirements here. Now, I'll just read through these quickly here. And I think there's 6 requirements. One is normality. That is, for each cell, the sample values come from a population with a distribution that is approximately normal. And this is robust against reasonable departures from the normal distributions. Also, variation. The populations have the same variance, or sigma square, or the same standard deviation, which is sigma. Again, this is robust against reasonable departures from the requirement of equal variances. Also, sampling. The samples are simple random samples of quantitative data. Of course, simple random sample means that samples of the same size have an equal chance of being selected. And then the other 3 on the next page, the samples are independent of each other. Okay. Now, we cannot use this procedure if samples lack independence. Also, two-way. The sample values are categorized in 2 ways. And this is the basis for the name of the method two-way analysis of variance. So in that table that I showed you, it was categorized in 2 ways, or 2 factors: age bracket and gender. And a balanced design, number 6, all the cells have the same number of sample values. This is called a balanced design. This section does not include methods for design that is not balanced. So if you looked at that table right here, if you count up the number of data values in each of these cells, there are 10. It should be 10 in each and every one of these. This is what we call a balanced design. Okay, because you must have the same number of data values in each of the individual cells in order to do this. All right, so here's the procedure for a two-way ANOVA. First of all, we look for the interaction effect. Now, we can use the 8-step hypothesis testing procedure to do this. Step number 1, we want the interaction effect. In two-way analysis of variance, begin by testing the null hypothesis that there is no interaction between the 2 factors. And then you're going to use technology to find the p-value corresponding to the following test statistic, which is this. F is equal to the MS, mean squares of the interaction, divided by the mean squares of the error. You won't have to worry about using this formula. It will calculate the F test statistic for you. And also, it will give you the p-value. Okay, so that's the importance of using technology here. And then for conclusion, we either reject the null or fail to reject. If the p-value corresponds to the above test statistic is small, that is less than 0.05, for example, or whatever level of significance that they give you, you're going to reject the null hypothesis of no interaction and conclude that there is an interaction effect. Or if you fail to reject the null hypothesis, That means if you have a p-value that is greater than whatever your level of significance is, we fail to reject the null hypothesis of no interaction between the two factors and conclude that there is no interaction effect. So if you reject the null, that means that there is an interaction effect. If you fail to reject, that means that there is no interaction effect. Okay. Now, in step 2, we look at row and column effects. If we conclude that there is an interaction effect, then we should stop now and not proceed with the 2 additional tests. So, if you reject the null here and conclude that there is an interaction effect, you are done with the problem. But if you fail to reject the null hypothesis, then you proceed to do the row and the column effects. Okay. So here we got the row factor. And also you'll find this in the output as well. For the row factor, you want to test the null hypothesis. There are no effects from the row factor. That is, the row values are from populations with the same mean. And then you're going to find the p-value corresponding to this test statistic. F is equal to ms of the row divided by ms of the error. Again, StatDist will do this for you. It will give you that F test statistic, by the way, for the row factor. And we'll talk about that when we do examples here. And of course, you'll reject the null if the p-value corresponding to the test statistic is small, or if the p-value is less than whatever your level of significance, you'll reject the null hypothesis of no effect from the row factor, and then conclude that there is an effect from the row factor. And then fail to reject if the p-value is large. And you fail to reject the null hypothesis of no effect from the row factor, and then conclude that there is no effect from the row factor. Okay, and now for the column factor is this. For the column factor, you want to test the null hypothesis, h sub 0. There are no effects from the column factor, that is, that the column values are from populations with the same mean. And then you're going to find the p-value corresponding to this test statistic. F is equal to ms of the column divided by ms of the error. Now, the StatDist would do that for you as well. It would give you the F test statistic for the row as well, and for the column as well. Now, you again reject the null if the p-value is small. That means less than your level of significance. You'll reject the null hypothesis of no effect from the column factor. You'll conclude that there is an effect from the column factor. And then fail to reject if the p-value is large. So if it's greater than whatever your level of significance is, you'll fail to reject the null hypothesis of no effect from the column factor and conclude that there is no effect from the column factor. Okay. Now, this is summarized in this flow chart that you see here. Now, in this case here, we start by testing for an interaction between the two factors. You'll use the p-value for that test statistic. And if the p-value is small or less than your significance level, you'll conclude that there is no interaction effect, that there is an interaction effect. Okay. So the next thing you ask yourself, is there an interaction effect due to the interaction between the two factors? And you have to answer either yes or no. If it's yes, you're done. So we won't have to do the row factor and the column factor. But if it's no, and you fail to reject the null hypothesis of no interaction effect, then you have to test the effect from the row factor and then test from the effect of the column factor, and then decide for each one whether you need to reject the null or fail to reject the null hypothesis. Okay, so this is that flow chart that you'll use. Okay, let's look at some examples here. The accompanying data table lists results from car crash tests. Included in results from car crash tests are loads in pounds on the left femur and right femur, and those values are shown in the table below. What characteristic of the data suggests that the appropriate method of analysis is two-way analysis of variance? That is, what is two-way about the data entered in the table? So here's our table here. And if you notice here on the left side, we got two types of femur, left and right femur. And we got three different types of cars: small, mid-size, and large. Okay. So you can see here that this is where a two-way analysis of variance can be used. Okay, and this is because, I'm gonna write this out, the loads, the load values are categorized using two different factors of the femur. That's, of course, left or right, and the size of the car, which is small, mid-size, or large. Okay. That's why we can use a two-way analysis of variance, or two-way ANOVA. Okay. All right, now example 2 is going to be this. Okay. All right, here we have this. Using the technology display, which results from the head injury measurements from car crash dummies listed below. Okay. The measurements are in HIC, which is head injury criterion units, and they are from the same cars used from the table below. Use a 0.05 significance level to test the given claim. And here I want to test the null hypothesis that head injury measures are not affected by an interaction between the type of car, foreign or domestic, and the size of the car, small, medium, large. And what do you conclude? So here's the table here that they give. Okay, the type of car, foreign or domestic, the size of the car, small, medium, and large. Okay. So in this case here, based on the information I'm given in this case here, our claim is going to be something like this. That head injury measures are affected by an interaction between the type of car and the size of the car. Okay, that would be the claim that I would use for this particular example. Okay, so here's the 8-step procedure that I would use here. So in step number 1, I'm probably going to need to use a different marker. All right, step number 1 is going to be this, the original claim. And I'm doing this based on the way the homework is set up and how the way it's written. So I kind of cheated a bit. So my original claim is going to be this, head injury measurements. And unfortunately, I'm going to have to write this out in words. Instead of symbolic notation. Head injury measurements are affected by an interaction between type of car and size of car. Okay, that's going to be the original claim. Step number 2 is the opposite of the original claim. Well, the opposite of are affected will be are not affected. So I'm just writing the statement as an opposite. So head injury measurements are not affected by an interaction between the type of car and size of the car, or the size of car. All right. And then step number 3 is just writing the null and the alternative hypothesis. Okay. Well, I think the null hypothesis that they tell you is this: head injury measurements are not affected by an interaction between the type of car and the size of car. That would be your null hypothesis. So in words, head injury measurements are not affected by an interaction between type of car and size of car. Okay. And then your alternative hypothesis, and I'm going to have to write the H1 in words as well. And that is that original claim there. Head injury measurements are affected by an interaction between type of car and size of car. So here we go. Head injury measurements are affected by an interaction between type of car and size of car. And this right here is the claim. Okay. All right, step number 4 is the level of significance here. And you're told in the problem to use a 0.05 level of significance. Okay. So alpha is equal to 0.05. And then step number 5 is the test statistic. All right, which is, of course, capital letter F, because we're using an F test statistic with two-way ANOVA, just like we did with the one-way ANOVA. All right. And we're trying to find out if there is an interaction between the two. So we look on the row that says interaction from this table or from this output. Read across under F, you're going to see its F test statistic, which is in this case 1.41. That's your test statistic. And then step number 6 is the p-value. Okay, so under the interaction row, we got 1.41 for the F test statistic. Here's your p-value for that, 0.281. Okay. And now step number 7 is our decision rule. If our p-value is less than or equal to alpha, we're going to reject the null hypothesis. So here the p-value in this case is 0.281. The alpha level is 0.05. And notice that 0.281 is greater than 0.05. That means we need to fail to reject the null hypothesis. Fail to reject the null hypothesis. And then, finally, step number 8 is our conclusion statement. Okay? If we fail to reject the null hypothesis and our alternative hypothesis was the claim, that means that there is not sufficient evidence to support the claim. Okay? There is not, because we failed to reject. There is not sufficient evidence to support the claim that head injury measurements are affected by an interaction between the type of car and size of car. Okay, that's our conclusion statement. Okay, but what can we conclude about this? We can also say here that there does not appear to be an effect from an interaction between type of car and whether the car is small, medium, or large. So I guess I can go ahead and write out what this means in another way. We can conclude that there does not appear to be an effect from an interaction between the type of car, and the type of car could be foreign and domestic, well, foreign and domestic, which is what we're talking about here. And whether the car is small, medium, or large. Or small, and I should say, yeah, medium. They say medium or large. Okay. Okay. Now this one had the table already there. Now notice that we failed to reject the null. That means we would have to do the row factor, test for row factor, and also test for the column factor. In this case, for this particular problem, that's all they asked for us to do. So we'll go no further than this on this example. But on the next example, we have the raw data. And this is where we're going to have to use StatDisk. Okay. Unfortunately, you're not going to be able to do this on the TI-83 or 84 plus calculator because those calculators do not have a special program for that, for the Two-Way ANOVA. I mean, it's out there, but you have to download it from your computer onto your calculator. Okay, so we'll have to use StatDisk for now. All right, the accompanying table lists post rates. Use a 0.05 significance level and apply the methods of two-way analysis of variance. What is the conclusion? Okay. So here we got a two-way ANOVA that we have to use because we got two categories here, gender and age. Age is separated by under 30 years of age and over 30 years of age, and gender is by male and female. Okay. Now I kind of looked at the problem and how it's set up in my math lab and what type of questions that they're asking for. And I'm gonna say this, that the claim is going to be this, that there is no interaction between gender and age. No interaction between gender and age. So step number one would be the original claim. And we're going to have to write this out in words. So in this case here, the claim for this would be that there is no interaction between gender and age. So I just write this out. There is no interaction between gender and age. And then step number two will be the opposite of the original claim. If there's no interaction, then the opposite means that there is an interaction. There is an interaction between gender and age. Okay. That's my original claim, and then the opposite of the original claim. Step number 3 would be the null and the alternative hypothesis. The null would be no interaction between the gender and age, because the null in this case means that there's nothing happening. So here, there is no interaction between gender and age. And forgive me for writing all of this out. And this is going to be your claim. And the alternative will have to be that there is an interaction between gender and age. So there is an interaction. All right. Now we can move on to step number 4. And that is the level of significance, which is going to be 0.05. That's what we will use here in this example. And then we're going to calculate the test statistic. Here we're going to have to use StatDisk. Okay. To come up with our F test statistic. All right, in this case, I'm going to show you how to use StatDisk to enter each of these cells for the row and the column, one by one, okay? So get ready. So let me go to StatDisk. I'm going to share my screen. All right, so you can see here, so you see what this is, okay? This is StatDisk. You just log in, go to statdisk.com, and if you haven't registered, go ahead and sign up for it or log into it if you already have it, okay? So this is what the StatDisk looks like. You should have sample editor. This is going to be blank, okay? Now, before we enter any of our data values here, we're going to first pull up the two-way analysis of variance. So on the blue ribbon at the very top, you go to analysis and then go down and find two-way analysis of variance, which is what we have right here. Okay, now on the left side, we got to do some things here. We need our level of significance. They give the default as 0.05. And our significance level that we're dealing with is 0.05. So we can leave that as is. Now, the number of categories for the row variable. Okay, now let me go back to my table here. If you look right here, rows go across. There are 2 rows. And also the column variable, the number of columns, there are 2 columns. Okay, so going back to this, the number of categories for the row variable will be 2. We just enter the number 2, and then tab down to the number of categories for the column variable. We got age under 30 years of age and over 30 years of age. There are only two categories there. And for the row, there was only two categories, male and female. Okay, now, number of values in each cell. Okay, now let's go back to this. If you take a look and count how many numbers there are in each of these cells, and in this case, there are 10 numbers in this cell, 10 numbers in this cell, also 10 numbers in that cell, and 10 numbers in the last one. Okay, so that means we go back to this and type in the number 10. That's the number of values in each of the individual cells that's on the handout for example 3. And then we click on Generate Table. Okay, it's going to fill in the row number and the column number. Okay, because you're going to have like row 1, column 1, and then you have to type in those 10 numbers, and then row 1, column 2, you'll type in those 10 numbers, and then row 2, column 1. Row 2, column 1, you'll type in those 10 numbers, and then row 2, column 2, you'll type in those 10 numbers here. Okay, these stay the same, but under the column where it says value, you're going to click on that cell, and then you're going to enter the female under 30 years of age. That's row 1, column 1. Okay, so in this case here, if you look at your handout, for row 1, column 1, female under 30 years of age, there are 10 numbers. We're going to type in 79 and then press enter. And then 104 and enter. Then 80, press enter. Then 63, 60, 99, 82, 97, 90, 97, and then enter. Now notice that the column numbers change because now you're going to enter data values from row 1, column 2. So it's going to be these data values, row 1, column 2. That's for female over 30 years of age. So we'll type in those values, 77, 77 again, 72, 67, 71, 78, 62, 73, 73, 56. And now notice this. We're looking at, we got 2 and a 1, row 2, column 1. You're going to be entering those data values here. So now you're going to be looking at male and then under 30 years of age. There are 10 data values for that. You'll type in those numbers. And in this case, for male under 30 years of age, we got 61, 80, 55, then 68, 68, 74, 75, 67, 62, 57. And now we got this, row 2, column 2. That's male over 30 years of age. You'll type in those 10 numbers. So in this case here, for male over 30 years of age, we got 46, 70, 63, 67, 90, 81, 59, 59, 63, and 60. And we're done. Okay, so once we typed in all those numbers, we will go ahead and click on the green button that says Evaluate. And at the very bottom, you do see the output. Okay, we have 3 rows here: the interaction row, row variable, and then column variable. So that's how we use StatDisk to use the two-way analysis of variance here. All right, now let me stop sharing this, go back here, and I'm going to show you the output. The row variable was for gender, as you can see, male, female. That's the row variable. The column variable was the age. The interaction is going to be this first row that I'm going to be focusing on. I'm going to get my test statistic here. That's your test statistic, which is to 2 decimal places, 3.73. Okay, so 3.73 is your test statistic. That's step number 5. Also, from that table, I'm going to get the p-value. So here, I'm just saying this using StatDisk. My p-value is equal to so from the interaction row, here's my p-value, 0.061 to 3 decimal places. 0.061, that will be the p-value. All right. And then my decision rule is comparing the p-value with the level of significance here. So here's step number 7. If the p-value is less than or equal to alpha, your level of significance, reject the null hypothesis. Otherwise, fail to reject the null hypothesis. So here my p-value is 0.061. The alpha level was 0.05. As you can see here, 0.061 is greater than 0.05. So that means we need to fail to reject the null hypothesis. Fail to reject the null hypothesis. And that claim is the null hypothesis. We're failing to reject it. So we're saying that there's not sufficient evidence to warrant rejection of the claim that the pulse rates are not affected by an interaction between gender and age. So here, in simple non-technical terms, there is not sufficient evidence to warrant rejection of the claim that pulse rates are not affected by an interaction between gender and age. Okay. Now here's the problem. Since there is not an interaction between gender and age, and we fail to reject the null hypothesis, we don't stop this problem right here. We have to test for the row factor, which is gender, And also we got to test the column factor, which is age. Okay. So we got to go through that 8-step hypothesis test for each one of these. So here we go with the row factor, which is in this case gender. And in this case, the claim is going to be that the row values are from a population having the same mean. Okay, so the original claim, and I kind of had to cheat a little bit because I had to look at the problem itself. So here the original claim is going to be that the row values, which is the gender, are from populations with the same mean. The same mean. And then step number 2 is the opposite of the original claim. That is, of course, at least one of the rows is sampled from a population with a mean different from the others. Okay, at least one of the rows is sampled from a population with a mean different from others. Okay. And then step number 3 is the null and the alternative hypothesis. Okay. So here, the original claim will have to be null hypothesis, because if it says the same mean, that means those means are equal. And of course, the null hypothesis always carry the equal sign. So we can say here that row values are from population. I'm just copying this over with the same mean. And then our alternative hypothesis has a statement where it has the word different. At least one of the rows is sampled from a population with a mean different from others. Okay. Now, step 4. Our level of significance is the same, 0.05. Nothing's changed about that. The level of significance is 0.05. And now step number 5 is, of course, the test statistic using StatDisk. And we're not going to, we're not going to use StatDisk this time, but the output from StatDisk gives us something that we can use. Okay, so I'm going to pull this up. This was the output that I printed out earlier, and it should still be on StatDisk, by the way. Now, we're dealing with gender. That's the row variable. Okay, let's get that test statistic from there. Here it is, 10.87. And we're going to round that off to 2 decimal places. So that's 10.87. Okay, that's the test statistic. Also, we can get the p-value from StatDisk as well. Step number 6 is the p-value using StatDisk, where in this case here, your p-value. And we're going to round this off to 3 decimal places. So for the row variable, which is your gender, here's your p-value. To 3 decimal places, that's 0.002. Okay. And then step number 7 is our decision rule. If the p-value is less than or equal to alpha, reject the null hypothesis. Well, the p-value was 0.002, and that alpha level is 0.05. Well, guess what? Our p-value is less than 0.05. Satisfies the decision rule, so that means we can reject the null hypothesis. All right, the claim was that null hypothesis, by the way, and I didn't even write that in. So this is your claim right here, the null hypothesis. We're rejecting the null hypothesis. That means we have sufficient evidence to reject the claim. So this is step number 8. That there is sufficient evidence to warrant rejection of the claim that the row values are from populations with the same mean. With the same mean. Okay. Okay. So we're doing the row, we did the row factor for gender. We also, and this is not the end of the problem, we also got to do the hypothesis testing, the 8-step procedure for the column factor. And the column factor is going to be the age column. Okay. So on another sheet of paper, I'm going to do the column factor. And that column factor is age. Okay. Now, my claim in this case will be that the column values are from populations with the same mean. So step number 1 is the original claim. And that's going to be this. The column values are from populations with the same mean. And then step number 2 is the opposite of that original claim. So here the opposite would be this. And it's going to be at least one of the columns, at least one of the columns is sampled from a population with a mean different from the others. Okay. That's step number 2. Now, step number 3 is writing the null and the alternative hypotheses. Okay, so in this case here, the null hypothesis, well, the column values are from population with the same mean. That means the means are equal. That has to be the null hypothesis. Okay, so the column values, the null hypothesis, are from populations with the same mean. And then the alternative hypothesis is just copying down the opposite. At least one of the columns is sampled from a population with a mean different from the others. Okay, so that's step numbers 1, 2, and 3. I know that's an awful lot of writing that I did here, but I just can't figure out another way of writing that using symbolic notation. All right, step number 4 is your level of significance. That's not changing. It's still going to be 0.05, as in the problem we were told to use a 0.05 significance level in the first place. Okay, so now step number 5 is your test statistic. So using the output from stat disk, here we go. We're going to be looking under the column variable, which is your age in this case. Read across, here's your test statistic right here. To 2 decimal places, that would be 4.79. Okay, that's your test statistic, 4.79. And also we can get the p-value from stat disk. So here the p-value from stat disk. Okay, the column variable is the age going across. to, let's say 3 decimal places, that would be 0.035. 0.035. That's your p-value. All right. And then step number 7 is the decision rule. If the p-value is less than or equal to alpha, reject the null hypothesis. So my p-value was 0.035. The alpha level was 0.05. So here we can see 0.035 is less than 0.05. Satisfies the decision rule. So that means I need to reject the null hypothesis for this. And then finally, step number 8 is my decision, well, the conclusion. Now, this is dealing with the column factor, which is age. So that means that there is sufficient evidence. And by the way, we rejected the null and the null hypothesis, and I forgot to write this down. Again, this is the claim. So here we're rejecting the claim. There is sufficient evidence to warrant rejection of the claim. That the column values are from populations with the same mean. Okay. Yeah. All right. And that is the end of example number 3. Okay. This is one of those examples where, in this case, when we're doing this particular ANOVA, two-way ANOVA, we have to look for the interaction between the two. If we fail to reject that there's an interaction, then we have to look at the row value, the row factor, and the column factor, and do hypothesis tests for each one of them. Okay. Okay, so we ended with example 3. Here's the last example. And trust me, this is the last example here in this video. The accompanying table lists measures of self-esteem from a student project. The objective of the project was to study how levels of self-esteem in subjects relate to their perceptions of self-esteem in other target people who were described in writing. The test here works well, even though the data are at the ordinal level of measurement. Okay. Use a 0.05 significance level and apply the methods of two-way analysis of variance. What is the conclusion? So this is a two-way ANOVA because we got target self-esteem, low or high in 2 categories, and the subject self-esteem in 3 categories, low, medium, and high. Okay. So now let's start with the 8-step hypothesis testing procedure. Now the original claim, here I'm going to be testing the claim that there is no interaction between the subject's self-esteem and the target self-esteem in determining self-esteem measures. Okay, that's going to be the original claim. So writing this out in words, that there is no interaction between the subject's self-esteem and the target's self-esteem in determining self-esteem measures. Okay. And now step number 2 is the opposite of the original claim. Well, if there's no interaction between the two, then the opposite would have to be that there is an interaction between the two. So there is an interaction between the subject's self-esteem and the target's self-esteem in determining self-esteem measures. Okay, so that's step number 2, the opposite of the original claim. Step number 3 is the null and alternative hypothesis. All right, if there's no interaction means that that has to be the null hypothesis. So I'm just going to say here that there is no interaction. I'm just going to say dot, dot, dot. I'm not going to write all that. But here, this is the claim. So your null hypothesis is a claim. The alternative is that there is an interaction. And again, dot, dot, dot. Not going to take the time to write all that out. Step number 4 is your level of significance. You were told to use a 0.05 significance level that's given to you in the problem. And then step number 5. This is where we have to use StatDisk to enter all that data. Okay. So here, there are 12 in each one of these. For the low, for the target and subject, low medium, there are 12, low high, there are 12. High low is 12, and you get the picture. So I'm going to go back to StatDisk. Let's see. Share. All right, what I'm going to do here I'm going to do this. Go to analysis, select two-way analysis of variance. The significance level is still going to be 0.05. That's not going to change. The number of categories in the row. Now, the target self-esteem had only 2 rows, low and high. So I'm going to type in the number 2 for the number of rows. But for the categories, for the column variable, we had low, medium, and high. Low, medium, and high. There were 3 categories there. So type in the number 3 and the number of values in each cell. In this case, that for each of those cells, there were 12 numbers. So I'm going to type in the number 12 and then click on Generate Table. Okay. And it does fill in the row and the column number. And then for each one of those, we have to put in the value. So like row 1, column 1 is going to be low and low. Okay. No, that's hard to see here on the small screen, but low and low has 12. So I'm going to type in those numbers here. All right, so I have 4, then 3, then 5, 5, 2, 3, then 5, 4, 4, 4, 5, and 2. Now, notice I have row 1, column 2. I have to look at low, medium, high. Low, medium, high. That's row 1, column 2. And I'm going to enter those 12 numbers in as well. So it'll be 2, then 2, 4, 3, 3, 3, 3, 3, 2, 3, 3, and 4. And then next is going to be row 1, column 3. Row 1, and then column 3. Low, high. Enter those values. You've got 3, 2, 3, 3, 2, 3, 2, 2, 4, 3, 3, 2. And then it jumps to 2 and then 1, row 2, column 1. Row 2, column 1, that's going to be high, low. That's these data values here, those 12 numbers in the high, low cell. So I'm going to enter those numbers. In this case, it's 2, 4, 2, 2, 2, 2, 2, 2, 3, 4, 2, 3. All right, and then row 2, column 2. That's the high, medium. That's this cell right here of 12 numbers. So in row 2, column 2, these numbers would go in 4, 1, 1, 2, 3, 1, then 3, 2, 3, 4, 1, 4. And then finally, you've got second row, third column. That's this cell right here. Second row, third column. In this case here, I have 3, 3, 3, 3, 4, 3, and then 2, 2, 4, 4, 3, and then 4. And we are done. So in this case here, we click on Evaluate, which is the green button. At the bottom, you do see the output for the interaction and then the row variable and the column variable. The row variable is the target self-esteem. The column variable represents the subject self-esteem. And I do have a hard copy of that output. And here it is. So the row column represents the target self-esteem. The column variable represents the subject's self-esteem. We're going to look at the interaction row for the F test statistic. And this is going to be to actually, I think I got that wrong. No. Okay, it's this one. To 2 decimal places, this will be 6.31. So my F test statistic is this, using StatDisk. My F test statistic is 3, not 3, it's 6.31. Okay. All right, now for the p-value, is this number right here. To 3 decimal place, that would be 0.003. Okay, so step number 6. Again, using StatDisk. The p-value is equal to 0.003. Okay. And then step number 7 is your decision rule, which is this: if your p-value is less than or equal to alpha, you want to reject the null hypothesis. Otherwise, fail to reject the null hypothesis. Well, that p-value is 0.003. And the alpha level was 0.05. You can get that from step number 4. You'll see that 0.003 is less than 0.05. So that means we reject the null hypothesis. Okay, and then step number 8 is going to be the decision, the conclusion statement. And the conclusion statement would be something like this, that there is this. We rejected the null and the claim was the null. So that means we have sufficient evidence to reject the claim. So here, there is sufficient evidence to warrant rejection of the claim that measurements of self-esteem are not effective by an interaction between the subject's self-esteem and the target's self-esteem. Okay. So we can also conclude that it does appear to be an effect from an interaction between self-esteem, the self-esteem of the subject and the perception of the self-esteem of the target. Okay. And guess what? We rejected the null hypothesis, so we don't need to do a hypothesis test for the row factor nor for the column factor at all. Okay. So this is an example where we just stop in this problem right here. Okay. Now, if we ended up failing to reject the null hypothesis, then we have to look at the row variable and the column variable and look at their respective p-values and test statistic. Okay. But here we just stop right here with that problem. And that will definitely conclude this video on Two-Way ANOVA. So feel free to send me an email or see me if you have any questions about this particular homework. I know that this was time consuming. It might be a little bit of a challenge for you. So try your best on the homework in my math lab, and watch this video as much as you need to. All right. Thanks for listening.